Okay, hello wonderful people of the internet, welcome back to another episode of Simuleos. I'm going to turn on the music on my side just a little bit. Okay, I hope you guys are all having a wonderful day. Anyone who might be lurking in chat, hey, thanks for being here. Already I can see that today might be a bit quieter. It's also going to be a lot shorter. So we're going to focus most of our effort on two things in particular. One, I'm going to focus on an issue that just popped up in the algorithm archive dealing with the flood-filled chapter. And then we're going to talk about the next chapter as I outlined in the last stream. The next chapter for the algorithm archive will probably be on epidemic methods, epidemic protocols, also called gossip mongering, as a tree or graph traversal method. And then from there, we're going to be moving on to other topics. Now, you might be asking, where's the Ray Tracing Saga? What's going on with that? Well, I just had a very long, probably 2-hour conversation with the other lecturers as to talk about what's going on with that particular ray tracing lecture, and we split it up into a bunch of different lectures that we'll be doing over the course of the next few weeks. So it's there. We're gonna come back to it, but for now, we don't. I'm gonna take a break from doing like actual ray tracing coding work today, and we'll start doing it again tomorrow. Again, I'm generally trying to do less MIT stuff outside of MIT working hours, so that's what I'm trying to do. And also, again, we have to make sure we have something coming out for the algorithm archive regularly. So again, we'll be doing epidemic methods and stuff like that. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know. And without further ado, I think we can go ahead and begin. Let me open up a Zernal PP page, do a little bit of bookkeeping, and then we can go from there. So I've been starting all the streams talking about Writing Wednesday. Tomorrow is Writing Wednesday. Also, this will be the last time I notify you guys that we do have Writing Wednesday coming up. So what is Writing Wednesday? Quite frankly, ever since I was a little kid, we'll say probably 10 years old or something like that, I've always wanted to be an author. To this day, I still want to be an author. And so I wanted to start incorporating some sort of creative writing into my weekly routine. And it just so happens that from 6 to 8 p.m., 6 to 8 o'clock p.m., it's just 6 to 8 p.m. in here, Eastern. I will be doing a creative writing stream with you guys. It might not be your cup of tea. I totally 100% understand that. But if you're interested in creative writing, you're interested in becoming a better writer, feel free to either show up during that time, or if you're really feeling like it, submit some sort of writing for me to read aloud during the stream. Otherwise, I'll just be reading my own writing and critiquing it and talking about what I think I did well, what I think I did poorly, and how to improve my writing from there. My plan is actually to follow up and keep going into National Novel Writers Month, NaNoWriMo, in November, but we'll talk about that as it gets closer. So this is the last time I will update you guys about Writing Wednesday, because now I think I've told basically everyone about the fact that it's happening. And I think we can just go ahead and hop into today's stream. So let's go over here. In particular, Lazy Prop here opened up wrote some code that we implemented, or that we used yesterday. That we merged yesterday. So this code was on the Python version for floodfill. So for those of you guys who don't know what floodfill is, let me go ahead and go to the floodfill chapter on the algorithm archive. So algorithmarchive.org. And if we go down to floodfill, should be here. Floodfill is the thing that basically fills up a circle in an R program. So if you have a little, a little bucket, you can drop the liquid in the bucket and it fills the contents of your circle. So for example, if we have a big black circle in here, we put a blue bucket on the inside, well, now the bucket becomes blue. That's the idea. Now, the way this works is by taking some sort of image and essentially decomposing it into a huge graph of elements that all go in different directions, right? So all of these elements are connected, and the idea is that we basically pick a point at the center of the graph, right? And we fill that point and also the neighboring points. And then we go to the neighbor and we fill those points, and the neighbors again, and we fill those points and those points and those points, until eventually we filled all of the points in the graph. And in the end, you'll get some animations that look something like this, where we see all of the points being filled in the circle. If we do it in a depth-first fashion, going through all of those elements in the tree, you just go as far as you can down to the left or right. And if we do it in a queue-first fashion, you're going to get something like this, where you see kind of it filling in a more, I don't know how to put it, but a more like, I guess, covering everything at once, like just all directions at once type of way. I'm not doing a very good job of describing it, but essentially With the Python implementation, there was something that was different with the Python implementation than with the Julia and C code. So with the Julia code, we have a color function in here. The color function has an inbounds check, and then says if the canvas location is not equal to the old color, we return. Otherwise, the canvas location is going to be equal to the new value. So the idea is every time we enter another pixel or something like that, we're simply going to say, hey, this individual pixel, what is the color of that pixel? If it is not equal to the old color, that is to say, if it's not a color that we need to change, then we return. If it is the old value that we're replacing, then we're just going to replace it with the new value, and that's it. And we do an inbounds check in here. However, the Python version did this all in one line. It simply said canvas of p is equal to new val. Now, what I'm trying to figure out is why they were able to do that while we had to do a whole bunch of checks. So let me take a look and see what we need to do. So we're going to cd into projects, algorithm archive, contents, flood fill, and let me first go to the Julia code, cd code, and then Julia. Ls here. We're going to vi floodfill.jl. So let me go down to color here, and we have an @inbound size of canvas location. Python rules. I don't think it has anything to do with Python being a better programming language or anything. I think it has to do with some programming logic because it's also in the C code. Okay, so what are we doing here? So first we are, okay. So I think the only difference is that the color here, the color function here does the bounds check. Let me see when I do inbounds. So I only do function inbounds here is in the color function. And then I also do it on find neighbors when we're querying for the neighbors. Okay, so we do it in those locations. So let's open up the Python code. So we're going to cd in projects, algorithm archive, contents, flood fill, code, and then Python. And let's go into vi floodfill.py, and they should also have an inbounds function. Okay, their inbounds function is also really ugly, but that's okay. Okay, so inbounds here, and so they do it when they're querying for possible neighbors. That's fine as well. Okay, so let's go here. So we do check the inbounds there. Now, I think the reason I did that was specifically because if we do the recursive fill in here, when we do the recursive fill, we don't have the ability to query for neighbors in the same way, I don't think. Let me see. Find neighbors is here. Actually, no, I think you're right. I think we go to find neighbors here. Yeah, we do an inbounds check there. Okay, good. Now, the other thing that they did is they let's see, so let's look at this find neighbors function, and here we're going to say if canvas possible neighbors equal to old val, then we put it into the set of possible neighbors. Okay, so I think they're actually right. I think we can just do function color, and we do a bounds check there. So do not color if not in bounds. So I think we can just do this, and I think it will work. So let's do write and quit. Let's go into vi floodfill.jl, move down here. And we tested it with everything, I think. Yep, we tested it with everything. So now let's do Julia floodfill.jl, just to make sure that works. All right, good. In principle, yeah, so all the tests still passed. Okay, so that's fine. So now this leads me to believe that we don't actually need to all code snippets for this chapter rely on exterior color function defined as the following. So in principle, we don't even need a color function anymore. We can just say, because now the color function is just one line. So in that case, we can just say canvas of location is equal to new value. So we don't actually need the color function. So I can actually change that here. So let's go ahead and get a PR up and running for this. So I'm going to quit here, get branch, get checkout master, get pull upstream master. All right, and now what am I going to do? I'm going to get checkout dash b, and we're going to say flood fill fix. All right, get and now we should have everything ready to go. So let's go in vi floodfill.jl, and now anytime we do the color function, we're just going to replace it with canvas of location is equal to new val. So here we're going to do canvas of location and what is it? Current location is equal to new val. Okay, and I can just delete that. Let's see, where else do we have it? Color, so it should be color canvas of location is going to be equal to new val. And let's see, we should have it in one more location. Here. So what was this? It was canvas of neighbor is equal to new value. Next, color. Okay, keep going. Canvas of location gonna be equal to new val. DD there. Next. Okay, so now we can probably delete this function, see if all the tests pass. So I'm gonna run it one more time. Julia floodfill.jl. All the tests pass, so that should be fine. So now I'm gonna go back one more directory, cd into c, ls here, and go into vi floodfill.c. And now they should also have a color function that we need to update. So color here. Okay, so what does this do? This basically say c.data of px plus cx, c.max. So what they're saying is that we don't need this. So let's try that first. So now we're going to do gcc floodfill.c /a out. All the tests pass. So let's go ahead and remove a.out for no reason other than I just feel like removing it. Yeah, floodfill. Now let's take a look at their color function. Okay, so they say c.data is going to be p.x struct point p plus, hey Alexor, how are you? Plus c.maxx. Okay, so that's the extents in x times py. Okay. Maybe I still do want the color function in this case, because it does some indexing. So maybe I do that. So let's do DT here, and let's go to change all the color functions. So we have one here. Next, we have another one here. Next, and we have another one here. Should be one more, I think. No, okay, that should be it. Right, quit. Let's try GCC again. Floodfill.c. Okay. Git checkout. Git checkout. Floodfill.c. Let's try that again. I screwed up. Let's go into vi floodfill. Let's go to color. The color function in here. It says. So again, we don't need this. We don't need that. We need C, and we need P, and we need the new value. So we don't need the old value anymore is what we don't need. Okay, so let's look for that again, color. So we don't need the old value. Sure. Next, don't need the old value. And again, we don't need the old value. Okay, so now let's try that again. gcc floodfill.c /a.out. Okay. And then in that case, for the Python code, we also don't need the color function, so we can update that as well. Now the question is, this would mean that the C code has a slightly different notation than the Julia code. Maybe, okay. That's probably fine, right? I mean, it's probably okay. LXOR programming language I can understand. Sorry that you couldn't understand the Julia code. Look, Audrey, hey, how are you? Okay. But I think maybe that's okay if the C code has a slightly different notation than the Julia code, right? I mean, so, okay, the issue is that the color function is only one line in Python and Julia. It's also only one line in C. So let me take a look at that again. vi floodfill.c. All it is C data. Maybe I just do this. Color. Yeah, maybe we just do this. And we just see what people say. Okay. I think I just DD there. Oh, I probably did that really wrong. Crap. Okay. Well, let's just see what happens. GCC floodfill.c /a out. Okay, well that's not gonna end. Crap. I should have saved it, but I didn't. All right, let's do this again. Git checkout floodfill.c vi floodfill.c, go down to the color function. Again, we don't need the inbounds check anymore. Pretty sure that was okay. Try this again. GCC floodfill.c /a out. Good. So floodfill.c again. Okay, so we didn't need the old value. All right. So we don't need the old value. So let's fix that. Here. Color. Yep. Here again. And after that, it's here. Okay, I see the issue. Yeah, I see the issue. Okay, so now we're gonna yank this, and we're gonna go down to the next color function, and we're just gonna paste it here, paste it here, paste it there, and that should be it. Okay, so let's go down to the next color function. This one takes C, current location, which should be this one. All right, DD, next. So this one takes C in current location. There should be current location over here. All right, next. And this one I think can just be deleted. So let's try GCC again. /a out. God, crap, you kidding me? All right, what am I doing wrong here? Git diff. All right, so let's do cdc, and now let's do git diff floodfill.c. Okay, so it looks like the only changes are there. So let's go into floodfill.c. Okay, so we're saying c.data. So the color here is c.data, and then let's see, it's going to be current location, new value. Wait, what? Point P, color C. So we have P.x. So we're reading in point P. Oh, I got P and C mixed up, I guess. Yeah, okay, let's do 93. Okay. So we have C data here. And the idea is C data. Okay. And then the color is going to be C. That's fine. Then its current location is going to be P. And then its current location. Oh, there were two P's and I'm just dumb. Yeah, I'm just dumb. Yeah, okay, that's fine. Let's look for the next one on 157. Here, and this should be current location. Alright, write and quit. Let's run GCC again. /a out. Okay, now everything passes. Great. So now we're going to cd into the Python code and fix that one as well. Alright, let's go to color. Here. And it's just canvas P is equal to new value. So canvas of P. All right, we can remove that. Next. New value. Next. Canvas of neighbor equals new value. D there. Next. Canvas of P. New value. Next. Okay. now it's just a color function. I think I did that first thing wrong. So let's go over here, cd back a directory into Python, git diff floodfill.py. And it looks like on line 32. Nope. I did do something wrong. Stack fill. I added in canvas of p is equal to new val, when it should have been canvas of current location. Okay, so now if I run Python floodfill.py, tests passed. Okay, great. So we're going to go back one directory, and we're going to go one more directory, go into vi floodfill, and let's look for the color function. Let's see. All code snippets in this chapter rely on exterior color function. That should be okay. Right and quit. Git status. Git add dot. Git commit. Okay. Dash M. Let's see. Fixing unnecessary color function. All right. Sure. All right. Git branch. Git push origin flood fill fix. Crap, you're right. Thank you. I do need to fix the other line numbers. In fact, all of the line numbers are now broken. That is okay. We're just going to have to do that one step at a time. So what I will do is cd back a couple of directories, vi floodfill.md. Thank you so much for bringing that up. So let's cd into code. And we're going to cd to Julia. Go to vi floodfill. Set number. Okay. So let's just look for method. So I'm going to look at all the different code snippets that we have in here, and we're just going to fix it up. So this is line 37 to 55. Oh no. I don't even know what lines I was going for. Finding all neighbors. So this first code snippet is probably for finding the neighbors. Yes, so it's find neighbors. And so this is going to be on lines 23 to 41. Oh man, it is what it is. All right. So the next one is going to be, let's see, it was on line 100 before. This is depth first, so it's recursive fill, so it's 92 to 104. The next one is going to be, let's see, I said 57 to 77. So this is now going to be 43 to 63. All right, the next one will be, let's see. Nope, that's not anything I need. 80 to 104. Qfill, so this is 66 to 90. And I think that's the last code snippet for this chapter. Okay, good. So let's write and quit, and let's go into vi c floodfill.c. Go up to the start and end method. Okay. So for the C code, I said it was on line 34. This is going to be for finding the neighbors. So this will be on line 28 to 46. All right, the next one is 180. It will be 174 to 189. All right, the next block, ooh, well, that's not gonna work, is it? So the next block is gonna be 85. It's 79 to 99. All right, I think there is one more block after this one. 155. So this is on line 149 to 172. Okay, great. So that should be it for the C code. Yep. Yes, that's fine. So now we're going to fix the Python code. CD backward directory into Python. ls here, vi flood fill, .py. Oh man, it's okay. We'll get this done. This is going to be 13 to 28. That is 10 to 25. Okay. So the next one is 58 to 66. That will be lines 55 to 63. No, that didn't work, did it? What was it, 63? Okay, the next one is, let's see, 30. So this is going to be 27 to 36. Thanks for the catch with the line numbers, by the way. And let's see, the last one is going to be for Q-fill, and that's going to be 41 to 56. So this will be 38 to 53. Right that. In principle, that should be what we want. So go back a couple of directories and then npm run serve, check to make sure that all the line numbers are consistent and everything is good. And then we can hop on to the next chapter for the algorithm archive for epidemic algorithms and stuff like that, assuming that this is good to go. Great, pretty excited. Let me get some water. Give it just a second to build. Okay, so let's take a look. Over here, paste it there. Now we have to hop down to flood fill. We should be here. Okay, so we have to check all the languages. So first we'll start with Julia. Good. Everything looks good, ending with an N block. Yep. Okay, now for Python. Okay, scrolling up. Python's a bit harder, but I think it's okay. Yeah, I think all that's fine. Right, good. So it ends with the return, so that's okay. Hey, Ravengan, thank you so much for the bits. I really appreciate it. I hope you're having a great day. Actually, I hope everyone in chat's having a great day. Yeah, feel free to talk about, you know, life, liberty, the pursuit of open source software, whatever you want. Totally fine. I just need to check to make sure these are the ends. So stack fill. Here, that's fine. Recursive fill. Oh, so that must be right. Well, no, not necessarily. I'm sorry. Yep, that's fine. Okay, and the last one is going to be for Q-fill. It should be q.put neighbor. Great. Okay, and the last one's for C. Again, C is easy to check compared to Python. Yep. Ooh. I feel like I'm wrong for stack fill. Oh, I'm in the wrong file. vi c floodfill.c stack fill. Keep going. Nope. Stack empty. Stack pop. Free stack. Stack fill. Okay. After free stack, void stack fill. Void stack fill. I'm missing a few lines for stack fill, so that's okay. We're gonna have to add some stuff there. So it looks like I'm missing. Is that one? Missing 2 lines on stack fill. Okay, cool. So we're gonna go into. Yep, floodfill.md. And I think I just have to go down. Where would stack be? Stack. Nope, that didn't work. Okay, so if this is an archive for many languages, there should be a place for MATLAB. Yeah, I mean, if you want to submit MATLAB code, go ahead. That's totally fine. We have MATLAB in the algorithm archive. I mean, it's right along there with the other esoteric languages, like, you know, white space and stuff. So there's a queue animation by using a stack. So I think what I want to do is change this to 102. Okay, and let's just see what that builds to. Yes, so that's right for stack fill. Recursive fill is right. Find neighbors is right. Everything else looks good. So let's go ahead and do cd backward directory, cd one more directory, git add dot, git status, git commit -m, fixing line numbers. Right, git push, origin, flood, fill, fix. All right, there we go. Esoteric, that burned, not at all. It is what it is. Okay, so let's go here. What is 765 algorithm archive here, and let's submit that PR. Again, I'm just gonna take a look at it, make sure that it is all okay. Right. Remove color function from flood fill because it is redundant. So this is a direct fix for what is this? Number 765. Because the color function is essentially a bounds check before coloring, and the bounds check is done upon querying neighbors. It's not necessary to check on color as well. Okay, I removed the function and the text associated with it. Okay, misspelled text, that's okay. Let's see, this should also 752 and 743. Let's see, what was 762, I believe? Oh, no, what was it? 752 and 743. Yep, and number 743. Okay, create pull request. Good. Okay, so that's one pull request created, which isn't great. Usually I try to minimize the number of pull requests on stream, but that's okay. Good. So I'm glad we did that. So for those of you guys who maybe just came in and weren't here earlier, what we were just doing was updating or fixing an issue in the algorithm archive where essentially flood fill had unnecessary functions and such like that. So since we only had a few languages, we could very quickly go and fix everything as needed. Okay. So that should be good there. Let me check the pull requests one more time just to check. Maybe issues? Yeah, okay, there's some issues there, but let's go here to pull requests. I thought I just scrolled through an issue that I thought was something we could tackle now, but I guess maybe not. Okay, so now we're going to talk about the bulk of today's episode, which is going to be on epidemic models. Models, I guess we'll call it an epidemic protocol, which is somewhat different than an epidemic model, right? And I'll explain the difference as well. Okay, let me check something. I got a notification on the side screen. 1 second. Okay, good. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, feel free to let me know, and I'll totally address it as soon as I see it in chat. Today's stream is going to be significantly shorter than the previous streams for a number of different reasons. The first reason being that, quite frankly, I don't, I was busy with meetings all afternoon, so I wasn't able to stream any earlier, and I'm not going to end past 8 o'clock. I'm putting a hard limit, or I'm not going to be streaming past 8 o'clock. Again, as I said earlier in stream, we will not be doing ray tracing on today's stream. We might do it again, not tomorrow, but on Thursday. If you guys are here specifically for ray tracing, I'm actually quite surprised at how many people came for ray tracing, but are not coming for other things. Maybe ray tracing is more exciting than I thought it was, but that's okay. What's happening with the Ray Tracing Saga is that I am rolling that, rather, we had a 1.5, maybe 2 hour conversation earlier today with the other lecturers for the course about what we're doing with ray tracing, and we decided that we would kind of roll it out over the course of the next few weeks so we don't have to do as much in each lecture because there's just a lot to cover for ray tracing in the next few weeks, and there's a lot of rich, just pedagogical details that we need to go through. So because of that, it will be again, rolled out in the next few weeks. And yeah, that's the plan. So I will be doing more ray tracing almost certainly on the weekends and stuff like that. But because all my free time is spent doing, again, ray tracing and stuff like that for the lecture course at MIT, I need to make sure that I also do stuff for the algorithm archive as well. I think it's amazing that there are a variety of contents, not just ray tracing. Yeah, honestly, I also prefer doing more like varied content. You know what I mean? Besides which, this is also really cool. It's just, I guess, maybe because everyone knows ray tracing, they liked that stream more. I don't know. It's just, I don't know. I don't care that much about viewership on Twitch. It's not that big of a deal. But it was nice, we were getting like 100 viewers each stream, a maximum of like 120 viewers or something like that. And that was nice. That's like 100 more viewers than we have right now. But at the same time, we don't need that every day. And I'm happy to just do things that I actually like doing, rather than doing things that the crowd likes, Okay, so a few weeks ago, we talked about Epidemic Protocols. Let's talk about where we're going with this, why we're doing it, and why it's interesting. So, firstly, what I'm going to be doing is I'm actually going to be rolling both Epidemic Protocols and also another thing called Affinity Propagation, which we'll talk about next time, or soon, maybe next week. Is that how you spell it? Affinity Propagation? We're going to be combining these guys into basically a viral video simulator. Viral video simulator. To explain how viral videos are kind of natural phenomenon in networks, like the network that you get from YouTube, right? So we're going to be combining these guys together. And to do this, I need to make a chapter on Epidemic Protocols and also a chapter on Affinity Propagation. So a few weeks ago, we covered Epidemic Protocols, described what they were, why they're interesting, and stuff like that. And so today we're going to brush back up on that, figure out what we need to do to turn it into a full algorithm archive article, and go from there. So without further ado, let's just jump into it. In Bellic, I'll still be here while I do assignments in the background. Cool, yeah, I hope you enjoy doing assignments, I guess. I'm not really sure. 1 second. Let's see. 1 second. I need to answer something. Sorry, I just got a notification from work. One second. 1 second, sorry. All right, let's keep going. All right. So Epidemic Protocols, what exactly are these? Again, these are slightly different than epidemic models. So I'm going to put not equal to epidemic model. Now, what an epidemic protocol is a very good way to describe graph, well, we'll say graph traversal, not tree traversal, graph traversal. This is one of the premier applications of graph traversal. So here's the idea. Let's say we have a whole bunch of people, and they're all just standing about. Person here, person here, person here. They're all just all around, right? Now, an epidemic model is essentially a way to describe how information is spread across a graph. And when we talk about information, we're specifically talking about, in this case, a virus, where we're presuming that a virus is spreading across these people. So we have these guys connected, maybe something like this. It doesn't really matter how they're connected. The point is that all of these people are interacting with other people in some sort of group. So the idea is this guy over here, or girl, has some information that they're passing to this guy, who's then passing information to this guy. And basically they can only pass information across the nodes of the graph, or across the edges of the graph, right? So in principle, there are 4 different types of people that you could have. You could have people who are susceptible to information. You could have people who are exposed to the information, and let me explain what that means in just a second. You could have people who are infected with the information, and then 4, you could have people who are recovered from the information, and again, I'll explain what that means in just a second as well. Recovered. Okay, so for the purposes of this model, these are 4 different ways in which you can send information across the graph. So you have susceptible people. These are people who are able to receive a message. They can pull information into their node. So they're called, so this is called a pull node. And that again, they can pull information in. They can receive information. Exposed people can both receive information, but also they can push information out. Infected people are not able to receive any information because, again, they already have the information at hand, but they're able to push the information. And then you have recovered people who have already gotten the message and don't really care to give the message out anymore, so these are neither push nor pull nodes. So in this way, you can consider a graph of people all connected in some form, and you can say that these people are somehow allowed to spread information throughout the graph. So again, we have a working model for this. We actually did this in class, and now I'm interested in turning this into an algorithm archive article, doing some animations and stuff like that. So as a brief summary of how this works, let's say that this guy over here is infected with information. This guy over here is susceptible to information. And in fact, yeah, he is susceptible to information. Well, that would mean that, let's say in the next time step, this person sends information to that person. And then, one second. And then this person becomes infected, right? Or is exposed to the information at the very least. Now, when he's exposed, he can then send information out to anyone else in the graph, anyone else he's connected to. So now he's going to send information out to this person or this person or this person, right? Now, just for the sake of the argument, we'll say that this person is recovered, so they can't receive information, and maybe this person is recovered as well. But this person is susceptible down here, so they become infected. Because this person was recovered and they couldn't receive any information, these guys are now safe because they're not connected on the graph. If there are more than one kind of information, it is needed to add STH, like infected with information A, cannot pull A, but can pull other ones. Yeah, so that's how this could work. So a very clear example of why you might want to do this is, for example, if these weren't people and we weren't really modulating the movement of a virus across a population, but instead we were modulating the movement of information in a network of connected computers. So instead of people, let's imagine we have a set of computers. So here we have a computer here, computer here, computer here, computer here, computer here, okay? And they're just connected via a graph. So something like this, okay? So what we could say is that B can only execute after A. So A must be executed before B can start, and both of them must be computed before C can start. So let's say that this guy computes A, this guy computes B, this guy also computes B, and this guy computes C, and this guy computes A, or something like that, right? So what will happen is A is first computed. The information is then propagated to B, and that information is propagated here, and here, and then here, right? Now, C can only execute if both A and B are active, right? So then B is going to be the next step. So B is going to be enacted. So it's going to say, well, I've finished my process and send that to all of the nodes. And then once C has received both a signal that A has been finished and a signal that B has been finished, then C can execute. And so that's one way in which you might use this method in a more computing sense. The idea is, again, you've got this distributed set of nodes, and you have to say, well, I'm not really going to execute any action. Like, I can't execute C until both A and B are done. So then you would specifically say, okay, well, I already know A is done, so I don't need to receive any information about A, but I do still need to know when B is done. So I need to wait until I get some information about B. So that's kind of a way in which you might use this process. Okay, so let's CD. We are now going to go over here, Control C, CD projects, CD again, CD projects, Simuleos, LS here, and now we're going to CD into epidemics. Over here, CD projects, Simuleos, and epidemic. LS here. Okay, so we did a lot of this. What is a screenshot even? Oh, okay, that's the epidemic curve. We did a lot of different visualizations here, and I'm trying to figure out what we need to keep. So let's first look at the code, and then we're going to try to figure out what we actually need to, provide an intuitive description for what's happening, and go from there. So let's go into VI, what did I call it? Okay, let's just remove remove graph test. I've got a lot of stuff here, and I'm not really sure what I'm looking at here. So lsstar.jl, and it looks like I have SIR test, so VISIR test.jl. Okay, so here's our simple SIR model with the epidemic algorithm. So we're going to have to modify this a bit, but I don't think it's so far off from what we need. So here we have a mutable struct person, and the mutable struct person just has whether they are susceptible, infected, or recovered from the information, and some sort of ID associated with it. They also have a set of neighbors, and then we have some sort of constructor for it. So then the idea is we have function infect, and basically it just goes to that person and says, if that person's SIR status is that they're susceptible to the information, we're then going to infect them. And then we're just going to go through all their neighbors and infect them as well. Now, this is a breadth-first search through the graph. And in principle, there's different ways you might want to propagate information through. But for the purposes of this conversation, I think we'll just stick with a depth-first traversal for now. So the big question comes with stuff down here. So the function SIR test. We have people is going to be a set of people for 1 to 6. So here we just created a graph of 6 people. And we connected said graph of 6 people. Now, the reason I'm bringing this up is because there's a couple things. So this algorithm touches on a couple of different things. So let's talk about it. The first of which is proper graph traversal. All right, that's important. Okay, so graph traversal is something that we haven't really talked about. Now, we did talk about tree traversal. And if we do a depth-first search over a graph, that's generally good enough. But this means that I probably want to have some sort of graph chapter in the algorithm archive. And in principle, I think this discussion about the SIR model, about the push-pull methods, epidemic methods, is perfect because I think it really does explain how, explain in a very concise way why graphs and trees are important and all this kind of stuff. So I think it's worth doing. So we need to think about what we actually want in the graph traversal chapter, in the graph chapter. And then after this, we need to talk about information spread. So then we actually have to create the chapter on the epidemic model. So let's go down here and let's give it some room. So then we'll talk about epidemics. All right, so I think today what I'm going to do is I'm going to read through whatever's left over that we didn't really cover last time about epidemic models and stuff like that, because I don't want this chapter to be focused on the epidemic side of things. I want to treat it as what is called, I want to treat it as what it should be treated as, which is basically an epidemic protocol, similar to how it could be called a gossip mongering protocol or something like that. It's just a protocol for network spread across distributed nodes. So the question is, do we actually want to talk about distributed computing? I don't know. Let's see. Also, chat's particularly quiet today. If you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know. MFF Bid, thank you so much for following. Really appreciate it. Okay, so again, we only have about an hour left in stream. So let's go ahead and go here and let me look up gossip protocol. And let's just see if there's something in here that maybe we missed before that we should probably talk about in a bit more detail. I think we did cover it sufficiently well last time, but there's probably a lot of stuff that we could do better. So I'm just going to read through this a bit today, and we're going to try to figure it out. And hopefully by the end of this week, we have at least a rough sketch for what we want to put into the algorithm archive for graph traversal and our epidemic model and stuff like that, or epidemic protocol. And then from there, hopefully we can go ahead and start writing and stuff like that. Again, most of the algorithm archive work will be done from 6 to 8 p.m. I will say that a lot of the MIT work might be done over the weekend, specifically because I have to get that work done, unfortunately. But I think I won't have as much to do once we finish the ray tracing session and stuff like that. So we'll see. Let me get some more water. Okay, so let's go ahead and start talking about it. So gossip protocol, okay, a gossip protocol is a procedure or process of computer peer-to-peer communication that is based on the way epidemics spread. Some distributed systems use peer-to-peer gossip to ensure the data is disseminated to all members of a group. Some ad hoc networks have no central registry, and the only way to spread common data is to rely on each member to pass it along to their neighbors. The term epidemic protocol is sometimes used as a synonym for a gossip protocol, as gossip spreads information in a manner similar to the spread of a virus in a biological community. The best part of that MIT course, which is an amazing course by the way, was to discover this channel. Oh, cool! I'm happy you think that. I'm gonna be honest. I really need to make more YouTube videos. That's why I'm really pushing to make sure that any time that's not on work hour time, from 6 to 8 p.m. I'm spending this time working on algorithm archive work and YouTube work and stuff that will actually, again, build meaningfully into future prospects. But I do appreciate that you like the content. And again, if anybody has comments, ideas, anything, just let me know. Chat's super quiet today, so there's absolutely, I can follow chat without any problems today. In fact, it might be one of the quietest chats I've had in, I think, ever. I mean, it's been a long time since I've had a chat this quiet, but that's okay. Some days are like that, and it's not a big deal. Okay, gossip communication. The concept of gossip communication can be illustrated by the analogy of office workers spreading rumors. Let's say, each hour, the office workers congregate around the water cooler. Each employee pairs off with another, chosen at random, and shares the latest gossip. At the start of the day, Dave starts a new rumor. He comments to Bob that he believes that Charlie dyes his mustache. Fair enough. At the next meeting, Bob tells Alice, while Dave repeats the idea to Eve. After each water cooler rendezvous, the number of individuals who have heard the rumor roughly doubles. This doesn't account for gossip twice to the same person. Perhaps Dave tries to tell the story to Frank, only to find that Frank already heard it from Alice. Computer systems typically implement this type of protocol with a form of random peer selection with a given frequency. Each machine picks another machine at random and shares any hot rumors. Scream, oh wait, I'm tired, fair enough. I've been stuck on an issue for 2 days, not feeling very talkative. Wait, okay, so for the record, I do apologize. I didn't mean to I wasn't trying to eke information from you guys at all. I wasn't trying to be like, yo, I feel bad because you guys aren't talking. That wasn't what I was saying at all. I was just saying that the chat's quiet. If you guys have things that you want to talk about, I can definitely follow. The past few days have been quite, I'm not going to say chaotic, but we had, on all 3 of my previous streams that I've done, we got up to 100 people watching concurrently. Which is a large number, and people are quite talkative at that scale, so sometimes I wasn't able to fully follow chat. I can definitely follow chat today. I've been stuck on the issue, not feeling very talkative. I'm sorry about you being stuck on the issue, though. I hope it's fixed at some point. So the issue with the term gossip is that the quality of service, i.e. complete and timely dissemination, is predicated on the requirement that each member does not discriminate and ensures prompt and dependable transmission of the data to every member of their own peer network. In a real office gossip scenario, not everyone is privy to the gossip that is being spread. Gossip, first broadcast, is discriminatory, and often participants are left out of vital or important communications. As such, the comparison to office gossip is not as good as comparison to the spread of an epidemic. Nevertheless, the technique of peer-to-peer communication is sometimes referred to as gossip. Okay, so here we've got a couple things that we want to talk about. The first of which is this peer-to-peer communication. How do we connect different nodes into said graph? That is one very important thing that we need to talk about, and I'm not really sure how we want to do that. So, many variants and styles. There are probably hundreds of variants of specific gossip-like protocols because each use scenario is likely to be customized to the organization's specific needs. For example, a gossip protocol might employ some of these ideas. The core of the protocol involves periodic pairwise inter-process interactions. The information exchanged during these interactions is of bounded size. When agents interact, the state of at least one agent changes to reflect the state of the other. Reliable communication is not assumed. The frequency of interaction is low compared to the typical message latencies, so the protocol costs are negligible. There is some form of randomness in peer selection. Peers might be selected from the full set of nodes or from a smaller set of neighbors. Interesting. And due to the replication, there is implicit redundancy of delivered information. So that was actually a bunch of interesting things as well. Because basically they say, obviously, epidemic models, which are just ways in order to explain how information is spread across a network, have a huge number of different ways in which these can be implemented, right? You could assume that information isn't appropriate. You could say that you need redundancy. You need to send information more than once or across different network strands and stuff like that. This is good. I'm glad we're reading through this, and probably we'll get a chapter as well associated with this. Yeah, see, epidemic algorithms. Come on. Anyway, let's keep going. Okay, so gossip protocol types. So it's useful to distinguish two prevailing styles of gossip protocol. One is disseminating protocols, or rumor mongering protocols. These use gossip to spread information. They basically work by flooding agents in a network, but in a manner that produces bounded worst case loads. Okay, this is good. There's a lot of information here that we have to kind of digest. Event dissemination protocols use gossip to carry out multicasts. They report events, but the gossip occurs periodically, and events don't actually trigger the gossip. One concern here is that the potentially high latency from when the event occurs until it's delivered. Okay, so event dissemination programs use gossip to carry out multicasts. So what exactly is a multicast? In computer networking, multicast is a group communication where data transmission is addressed to a group of destination computers simultaneously. Multicast can be the one-to-many or many-to-many distribution. Okay, fair enough. It just means that one bit of information is spread across multiple different final nodes. Right. I see. So here's the difference. So you have unicast, broadcast, multicast, anycast, and then geocast. Fair enough. Okay, so background data dissemination protocols continuously gossip about information associated with the participating nodes. Typically, propagation latency isn't a concern, perhaps because the information in question changes slowly or there's no significant penalty for acting upon slightly stale data. Okay, this is also important because here the idea is the network, for example, the information that you're spreading across the network. Let's say the amount of time it takes for, let me just scroll down here, for this computer to interact with this computer is long. So let's say this latency is long, right? In that case, you want to do more of the event-driven approach, where you say, okay, well, every time something happens, I then send information. But in the case where it's a short amount of time between these two different types of computers, or these two different computers, you might then say that we can just continuously send information. So every n nanoseconds, every n milliseconds, we just send and we pulse information out regularly. That's good. Good. Okay. So then we have protocols that compute aggregates. So these compute a network-wide aggregate by sampling information at the nodes in the network and combining the values to arrive at a system-wide value. The largest value for some measurement nodes are making smallest, etc. Interesting. So what is this saying? So these compute a network-wide aggregate by sampling information at the nodes in the network and combining the values to arrive at a system-wide value. The largest value for some measurement nodes are making smallest, etc. I might not be grokking that sentence appropriately. The key requirement is that the aggregate must be computable by a fixed size pairwise information exchanges. These typically terminate after a number of rounds of information exchange logarithmic in the system size, by which time an all-to-all information flow pattern will have been established. As a side effect of aggregation, it is possible to solve other kinds of problems using gossip. For example, there are gossip protocols that can arrange the nodes in a gossip overlay into a list sorted by node ID in logarithmic time by using aggregation-style exchanges of information. Similarly, there are gossip algorithms that arrange nodes into a tree and compute aggregates such as sum or count by gossiping in a pattern biased to match the tree structure. Interesting. What do we have here? You guys are making a botnet without me? I don't think we're doing anything with a botnet. Do you know where the word grok comes from? No, I don't actually. Grok. I just used it, but maybe I wasn't using it right. Grok is a neologism, is a relatively recent or isolated term, word, or phrase that may be in the process of entering common use, but that has not yet been fully accepted. Oh, interesting. Coined by an American writer, Robert A. Heinlein, for his 1961 science fiction novel, Stranger in a Strange Land. Oh, huh. I didn't realize it was that recent. That's kind of cool. Okay. Cool. Okay, so let's go back here. I think we need to think a bit more about these protocols to compute aggregates. Because, quite frankly, I'm not really sure what's interesting about this gossip protocol, about the epidemic models here, is that if you want to compute the aggregate of something, this might be an efficient way to do it, an aggregate over a network. This might be it. So many protocols that predate the earliest usage of the term gossip fall within the rather inclusive definition. Okay, for example, internet routing protocols often use gossip-like information exchanges. A gossip substrate can be used to implement a standard routed network. Nodes gossip about traditional point-to-point messages, effectively pushing traffic through the gossip layer. Bandwidth permitting, this implies that a gossip system can potentially support any classic protocol or implement any classical distributed service. However, such a broadly inclusive interpretation is rarely intended. More typically, gossip protocols are those that specifically run in a regular, periodic, relatively lazy, symmetric, and decentralized manner. The high degree of symmetry among nodes is particularly characteristic. Thus, while one could run a two-phase commit protocol over a gossip substrate, doing so would be at odds with the spirit, if not the wording or definition. Interesting. The second part is just magic space. An occult, stranger in a strange land. Very interesting. Actually, I'm quite interested by this. So, the term convergently consistent is sometimes used to describe protocols that achieve exponentially rapid spread of information. For this purpose, a protocol must propagate any new information to all nodes that will be affected by the information within time logarithmic in the size of the system. Okay, so I'm still not entirely sure what defines an epidemic or a gossip mongering protocol. See you, Trash Talk. Thanks so much for coming in. Have a wonderful evening, and yeah, I'll see you next time. Don't forget, tomorrow is Writing Wednesday. You probably didn't forget because you remember you're one of the people who are actually actively engaging in the Discord conversation. But yeah, so tomorrow's Writing Wednesday. We'll just talk about creative writing. In particular, at the very least, I'll read some of my stories, and we'll see if anybody else has stories to share as well. Okay. So again, I think there's a broad definition for epidemic models. So the issue here is that my understanding is that epidemic models are basically any way in which you can send information across a network. And there's a bunch of different ways to send information across a network. So the question is, which is the most stereotypical definition for epidemic models? Because again, everything is a rabbit hole, right? We can keep going deep and deep and deeper and deeper and deeper down this hole. But the question is, what do we need to give people the essence of epidemic methods before diving deeper into them later? And also, man, this is so cool. I mean, I know we just did it in class, but when I was doing it for class, I was, when I was teaching it in class, I was really focused on just getting something out, right? But now that I'm reading through it again, I'm just like, oh, this is super cool, and we're just doing it in my leisure. It's super cool, and I really want to talk about it more. So as much as I want to do big, huge videos on YouTube, maybe there still is a space to doing these kind of not as big methods, just talking about epidemic protocols and stuff like that, because this is so cool. This is one of the coolest things I've done recently, but I always think that every time we do something new, I always think that. Okay, so suppose that we want to find the object that most closely matches some search pattern within a network of unknown size, but where the computers are linked to one another, and where each machine is running a small agent program that implements a gossip protocol. So to start the search, a user would ask the local agent to begin to gossip about the search string. We're assuming that agents either start with a known list of peers or retrieves this information from some kind of shared store. Okay, so periodically, at some rate, let's say 10 times per second for simplicity, each agent picks some other agent at random and gossips with it. Search strings known to A will now also be known to B, and vice versa. In the next round of gossip, A and B will pick additional random peers, maybe C and D. This round by round doubling phenomenon makes the protocol very robust, even if some messaging gets lost or some of the selected peers are the same or already know about the search string. On receipt of the search string for the first time, each agent checks its local machine for matching documents. Agents will gossip about the best match to date. Thus, if A gossips with B after the interaction, it will know of the best matches known to B, and vice versa. Best matches will spread through the network. Okay, so here, again, the idea is that we have... Okay, so, we're searching for something on the network, right? So, I guess I'm asking how the best matches propagate back. On receipt of the search string for the first time, each agent checks its local machine for matching documents. Okay, so if the messages might get large, for example, if many searches are active all at the same time, a size limit should be introduced. Also, searches should age out of the network. It follows that within logarithmic time in the size of the network number of agents, any new search string will have reached all agents within an additional delay of the same approximate length. Every agent will learn where the best match can be found. In particular, the agent that started the search will have found the best match. I'm not convinced about that. Like, I need to think about that a bit more. For example, in a network of 25,000 machines, we can find the best match after 30 rounds of gossip, 15 to spread the search string and 50 more to discover the best match. A gossip exchange could occur as often as once every tenth of a second without imposing undue load. Hence, this form of network search could search a big data center in about 3 seconds. Interesting. That's really cool. I found out how to do code coverage on 4chan. That's cool. I have to go to bed with this feeling as it is already 1 a.m. here. See ya. Thank you so much for coming in. Have a wonderful evening. And yeah, I'll see you around next time. So gossip protocols have also been used for achieving and maintaining distributed database consistency or with other types of data in consistent states, counting the number of nodes in a network of unknown size, spreading news robustly, organizing nodes according to some structuring policy, building so-called overlay networks, computing aggregates, sorting the nodes in a network, electing leaders, etc. Epidemic algorithms. Gossip protocols can be used to propagate information in a manner rather similar to the way that viral information spreads in a biological population. Indeed, the mathematics of epidemics are often used to model the mathematics of gossip communication. The term epidemic algorithm is sometimes employed when describing a software system in which this kind of gossip-based information propagation is employed. Okay, so we've gone through a lot of information here. Let me try to just take a step back and hit the highlights and see how we want to actually tackle this when we put it into the algorithm archive. Also, guys, I do appreciate you guys being here. Again, if there's anything that you want to talk about in particular, just feel free to let me know, and I will, I'll address it as soon as I see it in chat. All right, let me get some water here. Nice, have a good one. All right, see ya, LD Hacker. Wait. Are you saying have a good one to Loca Padre? Yeah, I mean. Anyway, see ya. Okay, so graph traversal. Okay, so let's just talk about it. So we're going to create a new page, journal, new page before. And I'm just going to create a set of connected nodes. All right, so here's a set of connected nodes. I'm going to draw them all in white. So we have all these guys in here. And again, there's going to be a huge number of these. Again, they said hundreds of thousands or something like that. So these are all connected. And I'm just going to assume that they're just connected. Maybe all to all, like they're all connected to each other or something. Maybe not. Maybe they're just connected like this. It doesn't really matter how we connect them, I don't think, for the purposes here. The point is, we need to ask ourselves exactly how do we propagate this information about. If this is an all-to-all connection, meaning that every single one of these nodes is connected to every single other one of these nodes, then we run into a situation where it becomes increasingly difficult to send information to everything, right? So instead what you do is you just select a random subset of these nodes to send information to. So you might send information to this one, or to this one. Oh, this is really messy, isn't it? Let's try that again. So if this is an all-to-all connection, meaning that all the nodes are connected to all the other nodes, what you might say is that each node connects to a random subset of other nodes. So it connects here, maybe, and this one connects here, maybe, and this one connects here, or something. I don't know. Like, the point is that they're all connected in some way, and they basically choose their peers at random. Okay. So now the question is, I guess I've got multiple questions here. So what we're going to do is first we connect at random, we send information. Then those guys connect at random, send information. Those guys connect at random, send information. Every iteration, you continually connect at random and you send more and more information. So we should be able to do a really interesting visualization here where we do like an n-dimensional array, we'll say 2-dimensional array, and it's just filled with a bunch of connected nodes. And we just say that all of these nodes are connected and we just watch information start at this node and then spread at random to the rest of the population. And I think that's actually quite cool. I think that'd be an interesting visualization. So the other thing here is that there's multiple ways in which you can send that information out. I'm going to say for the purposes of the algorithm archive, we're going to stick with the most stereotypical example for this model, which is just connect at random, and propagate back that information. Chris O57A, thank you so much for following, really appreciate it. So I think this is what we'll call the epidemic model. Okay, so now the question is, what do we need in terms of graph traversal? Well, we need the concept of a graph, right? And in particular, I think we need to come up with the idea of a graph. When we talk about graphs, what do we need to talk about? I feel like we want to talk about adjacency lists and adjacency lists and matrices. I think that's important. 0xc45, thank you so much for following, really appreciate it. But also when we're talking about this, I guess we definitely need to introduce the concept of a graph. And the question is, what functions do we actually have to introduce? Probably some function to add a neighbor is probably necessary. So we probably want to talk about exactly what an adjacency list is, what exactly adjacency matrices are, and maybe for every language we want to introduce like the de facto, the standard graph, libraries that you use for that language. Okay, good. So we're kind of workshopping this, and so let's see. The next thing is for epidemics. Again, I think we're just going to do connect at random, and send information. Now there was something here that was mentioned, and I want to actually look into this. What I see code coverage a lot, but I thought this was specifically for testing. But then Locopadri just mentioned code coverage over here. So code coverage is a measurement of how many lines, blocks, arcs of your code are executed while the automatic tests are running. Code coverage is, I see, it's collected by using specialized tools. Yeah, so code coverage is something slightly different, I think. Unless, can you do code coverage via an epidemic model? I feel like no, you can't, right? I don't know, maybe you can. Anyway, I'm learning a lot today. I'm hoping you guys are learning a lot as well. And again, I really hope you guys are having a great day. So let's see. I think then this is essentially all we need. So we need to do a chapter on graphs, and we need to introduce adjacency lists and adjacency matrices. I suppose we need to create a good visualization for this as well. That's going to be a bit tricky. So this is step 1, right? Step 2 over here is just to go through and traverse through the graph. And again, we're probably just going to do this via depth first search or breadth first search. Right. Yeah, so that's what I thought. Also, I thought you left. But I guess welcome back. So let's see, this is 1, this is 2, and we need to talk about depth first search and breadth first search. Okay, so let's go back to this thing of what we want to talk about. So in addition to this, I also want to introduce affinity propagation. It's nice to debug or look, it's nice to debug or to look if all your code was run. Yeah, I knew that was what code coverage was, but for some reason when you said it before, I thought somehow it was maybe decided via some sort of epidemic protocol or something like that. But I think they're disconnected. Okay. So what am I going to do next? Oh, I see. You were just excited about something else entirely. Okay, I understand now. I got a shower and passed by to shut down my machine. Oh, okay, yeah. Well, welcome back for a few seconds and have a good evening. Okay. So the next thing I want to say, affinity propagation. So let's take a look at that as well, and let's see what we can do. So affinity propagation. Did I read the initial paper for this? Is this what I did? Okay. I must have read the paper for this, because there's no way this Wikipedia article gave me all the information I needed. So in statistics and data mining, affinity propagation is a clustering algorithm based on the concept of message passing between data points. Unlike clustering algorithms such as k-means or k-medoids, affinity propagation does not require the number of clusters to be determined or estimated before running the algorithm. Similar to K-medoids, affinity propagation finds exemplars, members of the input set that are representative of clusters. So in principle, we probably need a graph for this as well. Applications. A study comparing affinity propagation and Markov clustering to protein interaction graph partitioning found Markov clustering to work better for that problem. So the inventors of affinity propagation showed it's better for certain computer vision and computational biology tasks, e.g. clustering of pictures of human faces, identifying regulated transcripts and k-means, even when k-means was allowed many random restarts and initialized using PCA, principal component analysis. A study compared affinity propagation and Markov clustering to protein interaction graph. So here's the thing, whenever it comes to algorithms and stuff, there's just so many different things to cover. It is absolutely insane, and yeah, I'm pretty excited to cover these things. Also, like, what's going on today? Is everything okay? Like, I mean, no offense, but like, we have a 10th of, like, I don't know where everyone is. I guess I shouldn't be too worried about it, but yeah, I just don't know where everyone is. Okay. So, right. Okay, so then in this case, let's also talk about, let's see, so we have affinity propagation, and here we probably want to talk about a couple different things. We could also introduce k-means. I think most people probably care more about k-means than they do affinity propagation, but I just think for this particular problem, we wanted to use affinity propagation instead of k-means. So, yeah. Hey, Seagull Rush, how are you? I hope you're having a great day. Okay. So that's probably where we're at then. Let me scroll up here. So, what should we tackle first? I feel like the obvious thing that we should tackle first, since we just talked about epidemic methods, and again, we only have about 30 minutes left in stream. Maybe we talk about adjacency lists and adjacency matrices, because honestly, I don't think I've ever actually implemented my own adjacency matrix. The adjacency list is kind of what I have been doing before. So adjacency matrices are probably really good to talk about. I'm good, thanks. What's cooking today? We're just talking about the next chapters in the algorithm archive. Maybe introducing the epidemic protocol next. And we're talking about what's needed for that and what we need to do and all this kind of stuff. So it's a bit of a planning day, but we'll get back to doing, but we'll probably be doing like graph traversal and stuff next. We'll see. Let me get some water. Okay, man, okay, so this is telling me that pretty much everyone was just watching because of ray tracing. That's what I'm learning right now. And I guess that's fine. But yeah, it remotivates me to work more on my YouTube channel, which I just wish I had time for. So anyway, that's what we'll be working on right now. We'll be doing more YouTube stuff. Actually, when was my last video? Let me check that right now. YouTube.com, user, LeosOS. When was my last video was over 2 months ago, because I just didn't have, I have had no time to make videos since then. August 2nd, 2020. It's been over 2 months. And this is when I'm actively focusing on it as well. Okay, it's fine. It's fine. I just need to knock it out and get it done. Okay, let's go here. Right, so I guess maybe let's talk a bit about adjacency matrices. And yeah, maybe go from there. People are probably just busy on Tuesdays. I don't know, maybe. But like, we literally went from like, how many people did we have yesterday? So yesterday on stream, we had an average of 70 people on 65 people on stream yesterday. And today we have an average of, at best, 20. So we have like a third of what we had yesterday. And don't get me wrong, like I don't care that much about the numbers. Like it's not a big deal. But you know, when you're making content, you tend to care a little bit about what people think. And so today's been kind of slow. Didn't you get rated yesterday? Yeah, but the day before that we had, here, let me just bring up some channel analytics on the side here. So, okay, the day before that we didn't get rated. And, wait 1 second. Stream summary. Okay, so today our average viewer has so far been about 20. Yesterday we had an average of 60, and the day before that we had an average of about 70, and the day before that we didn't get rated. So And also, we only got rated at the very end of yesterday's stream. So, I don't know. You're right that, yeah, we did get a raid yesterday, but also, like, it's probably a bit more than that. I think people just aren't interested in the topics. Like, probably also, I mean, I wrote algorithms and epidemics. I thought epidemics would be interesting to people, but maybe not. I guess I'm just generally curious as to why people watch the stream, right? And so the reason I'm watching viewership is I'm trying to see, like, what people are interested in and stuff like that. Because I've got a bad habit. Couldn't you cut the streams? Oh no, I definitely can't do that. For YouTube videos, you mean? So the truth is, if I do that, I am lowering the quality of my YouTube channel to something I do not want to lower it to. There were a few times where I have done that in the past, and I'm just very unhappy with the quality of those videos. That's just how it is. They're just bad videos, and the way I see it is, I feel bad when I'm making those videos, and I already feel bad enough. So even though, yeah, it's been 2 months since my last video, it's just gonna have to be another month till the next one, because I'm very far away from where I want to be. I like watching to learn about a variety of programming subjects, nothing in particular. That's fair. I guess what this says is that, yeah, so, you know, when you're making content, you hope that people come back because they're interested in something that you do regularly, right? So, you know, you don't want to be just like, you could almost imagine the ray tracing in some ways to be like a viral hit on Twitch or something like that, which is fine. It's just that, I don't know, it's weird, you know, to go from, I don't know, it's just weird. And I think part of the problem is that because I can't actively do anything online, except for Twitch streams about my work, it's quite, I don't know how to put it. It's very taxing on my mind. Make a vlog, tour of MIT in the instructor zones. Nope, not doing that as well. That's also very low quality content. I'm not doing that. You're the Bob Ross of programming. I appreciate that. So okay, let's talk about YouTube really quick. Just really quick. I mean, why not? We'll ramble just a little, just a hair of rambling today. Where's that new page? Okay, YouTube. All right. So, oh man, try that one again. Let me just draw the arrow, because at this point, let's just draw a box, and inside the box, let's just draw a little triangle. Ah, for Pete's sake, little triangle. And you guys know what I mean. We're talking about YouTube. When it comes to YouTube, I have a general philosophy for how I make videos, and like the first rule of all of my videos is that I will not. So do not put out content I don't like, right? And that's just how it is. So all of my videos are videos I stand behind. They're videos I appreciate. They're videos that I think other people appreciate. Now, I will say, as I'm looking at my video content right now, I don't know why this turned in. I'm sorry about this. Like, my own insecurities turns this channel into like a rant and ramble session all the time, and I apologize for that. But if we go to the videos and we take a look at the most popular videos, right? Here's, you know, Understanding 4D the Tesseract. It's got 3.4 million views. I'm not super proud of this video. It's good. I like it, but also it's not my favorite video. Ripai, thank you so much for following. Really appreciate it. My next one is what is an eigenvector? What is a determinant? What is Monte Carlo? Impossible lenses? What is a fast Fourier transform? All of these videos I stand behind, besides maybe the fast Fourier transform video. But the point is, every single one of these videos, except for the egg video, I do genuinely like. However, the videos that I've put out recently, I put out one video. Let's see, what do we have here? I put out a video on... where is it? I put out a video on iterative function systems, followed by a video about how to make fractals with trees, which, by the way, is to this day the best video I have on my channel, period. This video on how to make fractals with trees is by far the best video I have. It underperformed. The reason it underperformed was because I just put out a video with basically the same thumbnail, but this is a follow-up, so I was hoping people would be interested, but they weren't. Then after that, I drastically dropped the quality of the videos, and I put out one on about a social problem with research software engineering. Then I talked about complex domain coloring, and then I talked about flood fill. Now, these 3 videos are the lowest quality videos on my channel, and I don't like them. They're fine. Like, I like them enough. Like, if they were from another YouTuber, I'd be like, yeah, that's a good video. But they're not for me. Like, it's just a bad video for me. And that's the thing. I've been slowly realizing that I'm not happy with putting out content that is subpar. You know what I mean? And that's just where I'm at. So even though it's going to take maybe another month until my next video, I'm doing that video right. And I'm tired of putting out content because it's fast. I want to put out content that I stand behind. And even if it's like, you know, it takes me another week or 2 weeks to make the videos, you know, I'm happy with that. Now I will say, well, thanks guys for subbing. Appreciate it. Here, I guess I can give you an actual link here. The other thing I want to point out here is that each one of these videos takes an insane amount of time, like an insane amount of time. This video here, how to make fractals with trees, that video took me 60 hours to make, and it's a 4-minute video. That's 6D hours. I mean, 6D hours for 4 minutes of content. Right? It's just an insane amount of work. And like, you get 5,000 views on it, you know? And so yeah, I do understand that I could just clip my Twitch stream, and probably that would be fine. You know, there's actually a whole bunch of really cool things we do on Twitch, and it's really funny and I enjoy it. But also, like, it just feels like low quality content. You know, talking about social things, like talking about like doing a vlog or a tour of MIT and stuff like that, that might be something that could potentially get clicks. But it also changes the type of content I put on my channel. And if I put that type of content on my channel, people might be expecting that type of content on my channel. And if they want more social commentary on my channel, they're going to be sadly disappointed, because that's not the main point of my channel. Now, you know, Writing Wednesdays. I might do a video on Writing Wednesdays, because I think creative writing is totally up the alley of things that I would put on my channel, because creative writing is very, very slightly different than the writing I do for the algorithm archive. So that's fine. It simulates, are epidemics as bad as academics? No. Epidemics are slightly worse than academics. Only slightly, though. Anyway, so that's my YouTube rant. I do apologize for that. I need to stop doing so many rants on Twitch. I just, you know, you get a bit, I don't know how to put it. You get a bit like, existential when you're doing streams like this. It might be nice to have the Twitch streams still going for slower phased talks, rants, and different vibes. I agree with that as well, but also we have a side channel where I put all that kind of stuff, right? So if you go here, I have my Simuleos channel here, and this is where I upload all of the YouTube videos for like 34 views. No one watches these videos. I'm actually interested to see what people said this time. Okay, that's fine. I don't know. It's fine. Twitch is more flexible. Yeah, I don't know. I just... The truth is, I'm doing everything I can to turn this thing, my online content, into a career. Because I'm just tired of my current job, and I really want to do something that I feel passionate about. And, you know, what got me yesterday is I did a 7-hour stream yesterday, 6.5-hour stream yesterday. And after doing a 6.5-hour stream yesterday, I was just burnt out. Like, I was so tired. But then I did 30 minutes of algorithm archive work where I just did a PR, and I was just immediately reinvigorated. I was like, wow, this is amazing. I was so excited about it. It just says something. It just says that I think my interests aren't... It really did open my eyes and help me understand where I want to go and where I am and how to get there, you know? So, you know, it is what it is. And I do apologize for all the rants and all the ramblings and all this kind of stuff. That's part of the shtick with Simuleos. I've been thinking about ways to make the Twitch channel a bit more like engaging and stuff like that. There's a lot of things that I've been trying to think of, or trying to do recently. And we'll just see what pays off and what doesn't. But the main thing is I need to start getting content out on YouTube. I need to start getting content out in the algorithm archive, because right now I'm not doing either. And no matter how many views the Twitch stream gets, I need to get more like, I need to get more views just funneled into the system so that we can see if I could turn this into a full-time career or not. Ranting Fridays? No, we used to have Fortran Fridays though. That was super fun. We stopped it after a while. But man, Fortran Fridays, those were fun days. Sure, if something makes you feel better, then no doubt. Right. Anyway, let me get some water. So it looks to me like we're probably going to have to talk about adjacency matrices and stuff like that. It's just, there isn't really anything interesting about adjacency matrices. I mean, maybe there's like a way to talk about the structure of adjacency matrices and make it like really cool and interesting, but honestly, I don't know, I feel like, how do we make adjacency matrices interesting? I mean, don't get me wrong, these are cool diagrams, right? Like, they look nice, and they're readable and understandable. But I just feel like we should be able, there should be some cool thing you can do with it. It's just, I can't think of anything. I feel like this might be something that we just make an algorithm archive for, algorithm archive chapter for, that we don't necessarily put on YouTube. Maddie4, thank you so much for following, really appreciate it. So let's see. Well, also, okay, so what is the advantage of an adjacency matrix over an adjacency list? Maybe it covers this? List. So I think so data structures. The adjacency matrix may be used as a data structure for the representation of graphs and computer programs for manipulating graphs. The main alternative data structure, also in use for this application, is the adjacency list. Because each... Okay, implementation details. Also, I feel like there is the question, because usually when I create trees and stuff like that, I don't really think about lists or matrices. I usually just like have some sort of set of nodes that are connected to other nodes. That's all I do, which creates an adjacency list in principle. Here we are. The main alternative to an adjacency list is the adjacency matrix, a matrix whose rows and numbers are indexed by vertices and whose cells contain a Boolean value that indicates whether an edge is present between the vertices corresponding to the row and column of the cell. For a sparse graph, one in which most pairs of vertices are not connected by edges, an adjacency list is significantly more space efficient than an adjacency matrix. Fair enough. Sort as a 2D array. The space usage of the adjacency list is proportional to the number of edges and vertices in the graph. While for an adjacency matrix stored in this way, the space is proportional to the square of the number of vertices. However, it's possible to store adjacency matrices in more space efficiently, matching the linear space usage of an adjacency list by using a hash table indexed by pairs of vertices rather than an array. Also fair. The other significant difference between adjacency lists and adjacency matrices is that in the efficiency of the operations they perform. In an adjacency list, the neighbors of each vertex may be listed efficiently. In time proportional to the degree of the vertex. In an adjacency matrix, this operation takes time proportional to the number of vertices in the graph, which may be significantly higher than the degree. On the other hand, the adjacency matrix allows testing whether two vertices are adjacent to each other in constant time. The adjacency list is slower to support this operation. Okay, so that's some good information. I guess the question is, how do we want to cover this? So we already have a chapter on tree traversal, and what we should really do is we should flesh out the data structure section in the algorithm archive to talk more about stacks and queues, and to talk more about graphs, and the subset of graphs, which are trees. And then maybe we need to talk about arrays, and different types of lists. So we need to find a way in which we can attack this. And that doesn't like slow us down too much in the future. So I think maybe we've talked about a lot of different things today. We've made some good progress. We've made a list of things to talk about, right? So let me go ahead and write that out. So today was basically a planning day, and I'm happy to do planning days. So let's talk about what we've planned. So what we know for a fact is that we need more data structures. So let's talk about data structures to update. So data structures. Right. So we need to talk about arrays, lists, graphs. Well, okay. Stacks and queues. Okay, so arrays, lists, stacks, and queues. Then we also need to talk about graphs, which will use literally everything above. It will use adjacency matrices, adjacency lists, stacks, and queues for tree traversal. That was meant to be an H, graphs. Okay. So this is a good set of what we'll need for data structures that we need to talk about. So what do we already have in the algorithm archive? Technically, we have 2 kind of skeleton chapters for these guys, but in principle, maybe what we need to do is we need to just go through, like just do a week on data structures, and we just tackle all the different data structures, and just from the bottom up, talking about like what's interesting about them, why they're interesting. Like for example, with arrays, there's a lot of interesting things that we could talk about in terms of like how we have the data aligned and stuff like that. And then after we talk about this, then we can move on to the next set of things, which would be tree traversal and graph traversal. So we already have tree traversal because that's easy. But then we have the question of graph traversal to extend that. Now, the reason graph traversal is slightly harder is because of the things that we just talked about earlier today with epidemic methods. Where we have to think about how we're spreading that information around. And then finally, at that point, we can talk about epidemic methods. Now, once we get to that point, we start talking about epidemic methods, we can then start doing our big application where we create like a video on how to make viral videos and stuff like that. Now, here's my issue. If I dawdle so much with data structures, I'm running into a situation where, again, I'm not going to be able to get a video out anytime soon. And so I've really got to think about how I'm going to do that. So maybe we put this off for a bit longer, and I think about what exactly we want to do for the next application. There's a lot of stuff to consider here. Bagwar007, thank you so much for following. Really appreciate it. Okay, so basically what I'm saying here is we've done a lot of stuff. We talked about a lot of stuff today. We talked about epidemic models. We talked about graphs and graph traversal. We talked about adjacency matrices and adjacency lists. Focusing on graphs, right? So okay. Essentially, what I'm proposing is the following. I'm proposing spending a full week on graphs. So 1 week on graphs. 2, we spend a week on the epidemic methods. 3, we spend a week on, probably want k-means, right? Followed by 4, which would be affinity propagation. Then we talk about week 5, which will be putting all of this stuff together into a YouTube model to talk about viral videos. And we can make the video how to make a viral video. Okay, so all that said, that means that that will be out on week 7. So that means my next video will be out in 7 weeks, at best. And now I know what you're saying. We could make intermediate videos, right? Like maybe we make a video on the epidemic method that might be worth doing. And maybe we do another one on the affinity propagation and k-means. You're right. So maybe this is what we have to do. We do we keep doing the short videos for a bit, and then we aim for a big video in the future, but we still have to get some content out, and that's just how it goes. So it looks like at best I can get a video out in maybe a week or 2. Okay, so let's do, so this is what we're gonna have to do then. We're gonna do in the upcoming next few days, weeks, whatever, we're gonna focus exclusively on graphs. That is to say, we're gonna buff up the data structure section in the algorithm archive specifically on graphs. This might turn into a video, it might not, but this is what we're going to build up to. So we start with graphs, we then move into the epidemic models, talk about k-means, affinity propagation, and then we just put it all into one big application. They'll come out at the end. This is like introducing elements of the puzzle. Right, I agree. This is how it goes. And then solving it. Yeah. So this is how it always goes with my channel. Like this is why all of my YouTube videos are significantly less complicated than what's on, like all my YouTube videos and everything on the algorithm archive is significantly less complicated than anything that happens, anything that's happened on Twitch. Because on Twitch, we know all this stuff. I don't have to stop and talk about it. I can just do this thing. But the issue is if I just do this thing over here with Twitch, then it never turns into a video because we don't have this, because we don't have any of the steps below to build into it. What language are we going to use? Probably still Julia. Okay. So this has been a really good discussion. I really do appreciate you guys being here, talking through it, even though, again, it's been mainly me talking to myself, but that's okay. I do appreciate it. And I think this is good. So we're going to hop into graphs, doing a deep dive into graphs starting Thursday. Tomorrow, we are going to talk about, actually, you know what? A deep dive into graphs could be actually a pretty interesting video if we do it right. I think there's a lot there that we could talk about, but I think that'll be it for today. Tomorrow we're doing Writing Wednesday. We're going to take a step back, do some creative writing on stream. I realize it's not everyone's cup of tea, but I really do want to do more writing. It's just something I do in my free time. And so I figure if some people enjoy playing video games in their free time, let me enjoy doing writing in my free time and sharing it with you guys. That's the plan for tomorrow. It'll be on Just Chatting. And then we'll be back on Thursday to talk about graphs. Probably we will also be doing more ray tracing on Thursday as well. And then on Friday, again, ray tracing and graphs. And then basically every day will just be a mix between ray tracing and graphs from that point on. Except for Wednesdays, again, which will be Writing Wednesdays. Okay, this was a really good stream today, guys. I think I learned a lot. I now understand where we need to go, how to get there, and we're just going to start tackling it one step at a time. And that will be it for now. So let's see. We have... let's see. What do we want to do here? How about we raid Tyanui again? He's really cool. Let's go ahead and raid him. So let's start that raid on TAIYOINOUE. And let's go. So thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos, which will be tomorrow. We'll be doing some creative writing. Should be pretty fun. And then hopefully on Thursday, we'll get back into ray tracing, followed by doing some deep dives into graph traversal and stuff like that. I'm pretty excited, and hopefully I will see you then. Bye, guys.